Welcome back, everybody. Today we're talking about a special type of equilibrium called solubility product equilibria. And for this type of problem, what we need to recognize from the get-go is that back in first term, when we learned about solubility rules, we said there were soluble compounds and there were insoluble compounds. And we expected for soluble compounds that they would dissolve completely in water, and for insoluble compounds that they stayed solid and did not dissolve at all. Here's the truth, though. Every compound will dissolve at least a little bit. So the ones that we label as insoluble are actually slightly soluble. Maybe you would even say very, very slightly soluble. So take something, for example, like silver chloride, which I have here. Silver chloride, if I put it into water, will mostly stay undissolved on the bottom of the container. So for instance, if you look in this diagram that we have here, we have solid AgCl sitting right there on the bottom. It's probably not the best color choice for me, so let's try something else. Again, at the bottom, you have a crystal lattice structure, AgCl, mostly in the solid phase. But if we look at it, we notice that there are certain ions, a few ions, that make their way into solution. They're dissolved, essentially. And in this diagram, they're represented by those individual ions that are not part of the crystal lattice structure. So for instance, right here, I have an Ag plus ion. Plus ions tend to be smaller. That's how I knew it was that one. And I have a Cl minus ion. And there's a constant kind of back and forth that's taking place between these dissolved ions and the solid. And so you'll notice things like this. The Cl minus ion right here is going back to rejoin the crystal lattice structure. It's becoming part of the solid once again. But on the other hand, I have another Cl minus ion that is leaving that crystal lattice structure and is going into a dissolved state. Likewise, I have here a Ag plus ion that is leaving the solid state and going into a dissolved state. And maybe at the same time, this Ag plus is also rejoining the solid. So it's a constant back and forth. We can set that up as an equilibrium equation with the solid on one side and the dissolved ions on the other side. Notice we don't include water within this equation. We just know that water is present because the ions are listed as aqueous because they're dissolved in water, and the solid is listed as solid because it is in that particular state. So we have a reversible reaction, and when you do that, you also have the potential for equilibrium. What we're going to notice is that some amount of this solid, we'll call it X, will actually dissolve. And we call that X the solubility of that particular solid. We're going to learn today through a couple of different problems how you would find the solubility of a particular compound expressed in moles per liter or molar concentration, and how you would find the individual concentrations of each one of the ions. But to do that, you need to have two things: an equilibrium expression, which we know is written as products over reactants. We call this KSP. SP stands for solubility product, but it's still just an equilibrium expression. So we would put our products in Ag plus. You do want to have that ion charge as part of the expression. multiplied by Cl minus. Either one is raised to a particular power because they have a coefficient of 1. And then you would put it over your reactants, but our reactants are solids. And we know in this case that solids and pure liquids are never included in an equilibrium expression. Now, fundamentally, for all of these ionic solids, the KSP is actually a known value. And you'll often run into tables that look kind of like this table right here that list a lot of different solubilities for a number of different compounds. So I could look up, for instance, silver chloride. Here it is right here. It has a solubility product constant of 1.8 times 10 to the minus 10. One of the big things I want you to notice about that is that it is very small. In fact, all of these solubility product constants are small, which means something that should make sense to us, that these are reactions that favor the reactants. They favor the left side. They favor the solid, because we're saying only a few of the ions actually make it into solution. So I have this KSP value of 1.8 times 10 to the minus 10. That's not its solubility, it's the solubility product. So what we're going to do today is learn how do we actually find the solubility of the compound, and how do we find the individual ion concentration. Well, we're going to do that with a different problem. We'll start on 2 slides down. One of the tough things for students here is knowing how to put the compounds together, but I'll give you a hint. Anytime you get a little bit confused or can't remember, go back and look at the KSP chart, and you're likely to find your compound. Here I have copper 2 carbonate. It's a solid. It's mostly insoluble. And so I'm going to list it as solid and then show how it breaks up into a few ions, Cu2 plus and CO3 2 minus. One of the big things that I want to focus on here is our ratios. So here I've got a 1, here I have a 1, here I have a 1. Everything's in a 1-to-1 ratio in this particular equation, and that's a big deal. Let's see why. So if I asked you what's the equilibrium expression for this, you would say KSP equals Cu2 plus concentration plus or times CO3 2 minus concentration. And we would just need to go back and look up what the value of copper 2 carbonate's solubility product constant is. So again, I look on this particular sheet. Here's copper 2 carbonate, and its value is 2.3 times 10 to the minus 10. So the question then becomes, okay, I can plug this in for my KSP, but what does that actually equal? Well, we know that some ions are going to be produced in solution. We don't know exactly how many ions are going to be produced in solution. So we would say that X of this is going to be made and X of this is going to be made. That's because they're in a 1-to-1 ratio. You technically could say X of this is going to break up. That's known as its solubility. But remember, we're not going to actually include copper 2 carbonate in our solubility or KSP expression. So I'm going to put in here for Cu2 plus X, and I'm going to put in here for CO3 2 minus X. So I have a pretty simple equation to solve. 2.3 times 10 to the minus 10 is equal to X squared. So if I wanted to solve that, all I really need to do now is to take the square root of both sides of the equation. When I do that, let's see what it comes out to. I have a calculator that may not be ready to do this, so let's see how it goes. 2.3 e minus 10 square rooted. And I get a value that I can write as either a decimal or in scientific notation. It's probably easier to write this one in scientific notation. So I'm going to write 1.52, 1.5 times 10 to the negative 5. And because that's a concentration, it's going to have the unit of molarity. This is equal to, as we just pointed out, the concentration of Cu2 plus, but it's also equal to the concentration of CO32 minus. Finally, because both of these ions are in a 1-to-1 ratio with copper 2 carbonate itself, we would say that copper 2 carbonate has a solubility that's also equal to X, or in this particular case, is equal to 1.5 times 10 to the minus 5 molar. Okay, let's come back together and give this a little bit of practice.